In this lecture, we're going to talk about how we can handle precedence and associativity, not by modifying the grammar, but by adding some extra support in the parser to deal with these two notions, which are quite important in a programming language. So if I'm doing shift-reduce parsing and I have an ambiguous grammar, an aspect of the grammar versus the language. So if the grammar is LRK, it can be parsed by some LRK method, then a parser might exist for that grammar. But if I wanted to create a grammar for that language, that may or may not be possible. So let me give you an example. If I have a dangling else problem, which means that I have a language which includes if then else statements, but it allows all the different types of ambiguities where the else can attach to any if, so it produces multiple parse trees. It might be possible to change the parser to handle the ambiguity so that we only get one output. So essentially what you're doing is you're changing what is acceptable by the grammar. So the grammar only produces one parse. Notice that the language doesn't change because the input string is still the same, right? So even though there is no unambiguous grammar for that particular language, we can change the parser, in particular the shift-reduce parser, can be changed, or some behavior can be modified in the parser so that it only returns one parse tree and it doesn't return all possible parse trees. For example, in the dangling else condition, you might say always shift instead of reducing, and if you do that, that means that you will always match the else to the closest if, or the innermost if. So let's look at this dangling else grammar in a little bit more detail. So we've seen this before, and we've seen how to make it unambiguous by changing the grammar, right? The language is not changing, the grammar is changing. But let's say I don't want to change the grammar. I don't want to make it all very complicated. I want to use this nice simple grammar because it's much easier to do code generation using these simple grammars. Then if I have a prefix, if E, then S, so there's two if statements, and then right after that I have an else right after this, right? So that's the next statement. So what should I do here? Well, if I look ahead and I see an else, if I shift, which means I'm going to eventually, if I shift this, I'm going to eventually use this rule, right? Because I'm going to have if E, then S, else, and then I'm going to have some S over here, something, it'll expand to some statement. And now I'm going to have to reduce using that second rule, because I have if E then S, else S on the stack, I reduce it. If I reduce, which means I take this and I replace it with an S, notice that now I get if E then S, else S. So I'm still using the second rule, but what's happened is this else is going to be modifying the higher if rather than the lower if, the closer if. So if we want to resolve this ambiguity using the sort of obvious heuristic, then all I have to say is always shift on an else instead of reduce if you have a shift-reduce conflict. And that will give me the right unambiguous tree structures every time. And all I had to do was introduce this heuristic into the parser rather than changing the grammar. So you can see it has this kind of appeal to it. The grammar stays simple. The parser is only a little bit more complicated because we've just added this heuristic to it. So this dangling else is ambiguous, but I can modify the parser so that I can get only one tree out of it. So preferring the shift over reduce resolves the ambiguity, but there is no real LRK grammar. Like if you just run the grammar through the LR1 table construction algorithm, you're going to get a conflict. It's just that we're going to resolve the conflict by just preferring to shift over reduce. Let's look at arithmetic expressions. So another case where you can use precedence, or you need precedence and associativity. So in this case, if I have ID minus ID, and I have already reduced this ID to an E and reduced this ID to an E, and I have a dot over here. If the dot is before the multiplication, if I reduce, I would get what is considered to be the incorrect precedence, right? I want to have the multiplication happen first according to the conventions of precedence in arithmetic expressions. So in this case, the right thing to do would be to shift on the multiplication. So if I'm looking in both cases at one symbol of look ahead, which in both of these cases is the multiplication symbol. So if I guess there is like a line missing here, so I'm just going to draw that. And if I wanted to do left associativity, and if the next look ahead symbol is a minus, then what I want to do is do a reduce, and I get a left branching tree, which is what I want. I want it to be left associative instead of right associative. So in some cases, I want to do a shift, and in some cases, I want to do a reduce, but I can use this symbol of look ahead, right? I can look ahead and see, is it multiplication or subtraction that's happening? So again, I'm just so now the trees look more complete. Okay, so let's look at how we're going to implement this in the shift reduce parser. How can I do a shift or reduce by looking at this symbol of look ahead? So let's use a notation. This notation is slightly different from what we use in Yak or Bison, but it's a little bit more precise. So I prefer to use this one instead of what is used in Yak and Bison. And you'll see the reason is it gives me a little bit more control over the precedence and associativity rules. So let's say that A goes to W is a rule in the grammar, B is some terminal symbol, and some state of an LR1 parser there is a shift reduce conflict. So you can either reduce with A goes to W or shift on a B. Then what we do is we write down alongside the rule, we write down this extra bit of information. And this extra bit of information is going to provide us with both precedence and associativity information. So if I have a rule, A goes to W, and I have this less than sign, so less than B, it means that the rule has less precedence. So we're transferring the precedence in terms of operators into a decision about shift versus reduce. So if the rule has less precedence and the next symbol is a B, we're going to shift on symbol B. You're going to shift B instead of reducing using A goes to W. And if it's greater than B, which means that the rule has higher precedence. So if I see a look ahead, in my look ahead I see B, then I'm going to prefer to reduce using A goes to W rather than shift. And if there are multiple terminals with shift reduce conflicts, you can actually tack on as many as you want. So here it says that the rule, if it sees a B in the look ahead, it has higher precedence than the terminal symbol B, so I'm going to reduce. It has less precedence than C, so if it sees C, it's going to shift. If it sees D, it's going to reduce. So each of these rules here tell me what to do in the context of a look ahead. Should I shift or reduce? So it all boils down to telling the parser, if there is a conflict, then what should I do? So this lookup table tells me, if the next symbol is B, I'm going to reduce. If the next symbol is C, I'm going to shift. So let's look at a more concrete example. So let's look at the expression grammar that we're familiar with, and which, as we know, is highly ambiguous. It has many, many trees that you can associate with the input. And we can write the precedence rules in this very simple format. So it says, if I have a rule E goes to E plus E, if I see a plus as a next input, as a next symbol of look ahead, then I'm going to prefer to reduce. If I see multiplication, I prefer to shift. And if I have multiplication, so E goes to E times E, it has higher precedence than plus. So if I see a plus, I'm going to reduce. And if I see a times as a next symbol, I'm still going to reduce because I want it to be left associative. So let's look at the LR1 table that you would get. If I have this grammar, at some point I'm going to end up with E goes to E times E, and I move the dot across the E, I'll get the dot over here and the dot over here and here. So in this case, I'm in some state 10, and there's going to be a shift on a plus, a shift on a times, and I have a reduce using this rule, rule 2. Like this is reduce using rule 2. Similarly, I have a state where I've moved the dot across the E here and here and here, and it also has a shift on a plus or times, and this is doing a reduce using rule 1. So let's look at how to write down the precedence and associativity rules. If I have rule 1 over here and rule 2 over here, then we saw that if I have a plus, I'm going to, as an X symbol, I'm going to reduce. If it's a times, I'm going to shift. So if you look at this state 7 that we're going to write down into the table, ordinarily there's a shift reduce conflict here, right? No matter what I do, this reduce is not going to be less ambiguous even with the look ahead, because this E goes to E plus E can occur in the context of a plus or a times, right? The grammar is highly ambiguous. So, but if I look at these rules over here, I know that in state 7, if I have E goes to E plus E, if the next symbol is a plus, then I should do a reduce using rule 1, right? So that's what you can see from the definition here. And if it's a time multiplication operator, then I do a shift to this state, whatever the state is. So let's say the state was, I don't know, let's say 8, then I would shift to 8. Now let's look at 10 and state 10. If I have a plus, I'm going to reduce using rule 2. And if I have a times, I'm going to reduce using rule 2. So this handles a case where multiplication has higher precedence. It also handles a case where it's left associative. So this is implemented in Yak and Bison using this ordered list of percent left or percent right declarations. But those are the same precedence is applied to the operator no matter what the rule is. So this notation that I've used is slightly more flexible, although probably more confusing for a programming language, because typically you want the operator to have a certain precedence. You don't want it to have a different precedence rule depending on which part of the grammar it is, right? So it makes sense. That's why Yak and Bison implemented it that way. But this notation gives you slightly more control. Like you can use a different heuristic depending on depending on which rule you're applying it to, right? And it's general enough that it subsumes or incorporates whatever is done in the Yak and Bison. So as a question for you, I would like you to write the precedence and associativity declarations for a regular expression grammar. And you can do it either in the Yak Bison notation, although it's a little bit easier to write it in this notation that I've shown you here. But you can try either one, just as long as you understand how to modify a shift reduce parser to deal with precedence and associativity.